In today's lecture we will talk about circular and rotational motion. So far we have been dealing with motion in a straight line mostly, except one example where we have analyzed the speed of the ball that was thrown to the horizon. So except this one example, we were dealing with motion in a straight line. Now we will discuss one topic about circular and rotational motion. So let's begin with uniform circular motion. This is kind of motion where when object is moving in a circular path, but at constant speed. So V is constant. If you have here some kind of center, then there is some kind of circular path that, let's say the object, some kind of object is going around this circle. So the direction of velocity is like this. So here, he is traveling with the same speed, but what's happening is that so here we refer to speed, V constant, okay? So the velocity has direction to this. Here the velocity has direction here. Here the velocity has the direction here. Direction is with this circular path. Here it has the direction here, and the same thing happens here. So you see that velocity, as you remember, is speed and direction. Here it is moving with constant speed, constant. But what's happening? Direction changes. Although he's moving with constant speed, the direction changes of velocity vector, therefore acceleration is not equal to 0. There has to be some kind of acceleration. And imagine that you whirl a stone on some kind of string. The stone is tied to some kind of string. So here is the string, here is the stone, and you just whirl it around. And imagine that this string breaks. So what's happening with the stone, let's say at this point? At this point, if the string breaks, the stone would move at a constant speed in what direction? The direction would be straight line, so he would move in this direction. So there would be no force and no acceleration. If there is no force, it means there is no acceleration. So the path of an object is, it moves with a constant velocity. That means it moves at a constant speed in a straight line. In this case, the object is moving around, so the direction of velocity changes. Although the speed is the same, direction changes, so there has to be acceleration and there has to be force. So because F is equal ma. So the force that is holding this object in this circular motion is called centripetal force. Centripetal force, and the acceleration is called centripetal acceleration. So the direction of this force is to the center of this. So here would be F. This F, let's call this FC. The direction of force would be to the center of the circle. And the direction of acceleration would be to the center of the circle, because the direction of force and acceleration, they coincide. So here the direction of force is to the circle, center of the circle, and the direction of acceleration others coincide. So centripetal acceleration AC is equal to v squared divided by radius of this circular path, of this circle that the object is moving around. So v squared, this is v, and divided by r, and centripetal force is equal to m AC, centripetal acceleration, so therefore it's equal m v squared divided by r. So you can see that if acceleration increases, if speed increases, it's squared even, and if r increases, acceleration decreases. Here in this case, if you whirl a stone tied on a string, imagine that you whirl it above your head. So centripetal force, if you whirl a stone, above your head, doesn't matter, above your head or around you, around your body, whirl a stone above your head, tied on a string. If you whirl a stone tied on a string above your head, then centripetal force is provided by the tension of a string. So the tension of a string is provides a centripetal force. Imagine another situation that you have that the car is moving in a straight line, and then the car has to make a turn. So let's say the car is driving here. Let's draw a primitive. It's maybe. So let's maybe not. I will not draw because. So here it is V. The direction of V. So here it's V. Here the V. You see changes. So here the direction of V, because the road is not straight, so that a car and an object is moving not in a straight line, so the direction of speed changes. So it means that there has to be here some kind of centripetal force, and this centripetal force is going to the center of a circle, and also there has to be centripetal acceleration. Centripetal acceleration, according to the Newton's second law. Here, if the car is moving, maybe draw this primitive car. If the car is moving to this direction, so the centripetal force is provided by the Fc, provided by friction, which has this car with the road. If there is no friction, if the road is slippery, then the car may go out of the road. So this motion would be like we have shown of the motion of a stone. So if there is no centripetal force, this car would go like here, out of the road. And is a very good example of Earth and the moon. The moon is going, let's draw it some kind of circle. The moon is going in a circularly. For simplicity case, let's hold it circularly around the Earth. So the moon is going circularly around the Earth, so there we can draw the moon. So Earth's gravitation provides the centripetal force. So here in this case, centripetal force is provided by Earth's gravitation, so the moon is going around. The speed, as we have shown on the previous picture, the speed of the moon is like going to this direction. There it goes to this direction. There it goes, here it goes to this direction, and here it goes to this direction. If here, imagine if here the moon is going here, at this point, if this centripetal force disappears, what happens to the moon? There is no force, so the moon is going in a constant speed, in a straight line, so moon goes to space, goes out to space, so there is no moon. So these were the first astronomical thoughts, observations of early astronomers and mathematicians, and when they connected all this Newton's insights into this astronomical science. Now, with this rotational movement, rotational motion, there is a thing, a quantity, angular, or sometimes called rotational velocity. So what's happening in this? So if you have not very good circle, but let's something like circle. So if you have, we don't need this a perfect circle to be here. If you have radius r of a circle, and you have point A here and point B here. So, and these points, they move, let it be an angle phi. So, as you can see, this A object, what is the length of the path that this object A travels? Object A travels, so it travels a path L 2pi r. So the length of the path, so it is the length of a circle, 2 pi r, and it is the speed would be 2 pi r divided by delta t, by the time that it, or just time that it has traveled. Okay, delta may be not important because it travels, let's say, from the time t1 equal to 0. So v is 2 pi, because v is what is L divided by t, or delta, let's say right here, delta L divided by delta t, or just simply v is L divided by t. So what happens for object A, so let's say here not object A, but just object travel. So object A, so object A travels what path? Object A travels this small, let's write this small r. It's from here to here, this small, because it's here, this object position. So object A travels 2 pi r small divided by t, while object B, it travels whole this big. So VA, VB, it travels 2 pi r big divided by t. So as you can see, in the same time, object B travels at the highest speed, because it has a bigger path to go, although the time is the same. So it has to travel at a bigger speed. So therefore, the speed, that conventional speed is for circular motion is not so optimal. Therefore, we have therefore angular speed comes into play, and what we have here is this angular speed can be written as omega. So, and it is what it is, this angle that object A or object B travels, angle delta phi divided by delta t. So therefore now object A and object B, they travel the same angle. Doesn't matter the radius or length from the center of a circle that these objects are. So in this case, omega A and omega B are the same. So omega A is this, omega B is this, and they are equal. Omega A is equal to omega B. Therefore, we can define that angular speed is omega delta phi delta t. And now, similarly, we can define epsilon. Epsilon would be delta omega, delta t, this would be angular speed. This would be angular acceleration. Angular acceleration. How much angular speed changes in time. So we have angular rotational velocity and we have acceleration, okay? Okay, what now? So this angular that we talk angular velocity or acceleration, it is equivalent in circular motion or rotational motion. It is equivalent to, as we agreed, as we were talking previously, linear, not angular, but just traditional, conventional, it's called maybe linear acceleration and velocity. So here it is the analog. Now torque. If you have some kind of let's say you have a something that can rotate, so torque, it is connected to rotational motion. And let's say if you want to open the door, so if you want to open the door has hinge here, it's connected to the wall, and if you want to open the door, this is a rotational movement. The door rotates around the position where it is built, and if you want to open the door, then you have to or close the door, then you have to pull it further away from the hinge. So let's say here, you pull it here, and here is easier to close or to pull. But if you put a hand somewhere here close to the hinge, it's not that easy to push or to open the door, let's say, to pull the door. So therefore, in this case, it's easier. So here are the distance. The door is moving in a circular motion. So here is the door, and it's moving in a circular motion. So R, as we call it here, as longer when R increases, the equivalent of force increases. So therefore, in rotational motion, there is equivalent to force called torque. So we are going to define this thing of torque, and then it will become easier to understand. Now let's say you have some kind of object like a rod, and here it is axle. It can rotate on this around this place, around this axle. It can rotate, move to this side or move to this side. It's rotational motion. It can turn. So if you apply force here, so you know that only if you act on here somewhere the force, or here somewhere, this force doesn't. If you act to this direction, it doesn't. If you apply force to this direction, it doesn't produce rotation. If you apply force to the axle, it doesn't produce rotation. If you apply the force here, then it moves clockwise direction. Yes. If you apply force here, it moves also clockwise direction, down. So in this case, although these forces are opposite, but they make the rod go in this clockwise direction. So in this case, although the directions of force oppose each other, but they provide the same direction. So because it is rotational movement, that's a bit different thing that we were talking about, but you understand this. It's easy in everyday experience. So now what's happening here, and if you know from this example or your experience, just as if we compare force applying to this point, let's say FA here and FB here, so equal the same forces, but one applies to this point, one applies to this point. So as compared with the door, so you will need to, in order to open the door or to close the door, if you apply force to this point, close to the hinge, then you will need a higher amount of force. If you apply to this point, like B, this would be B8, this would be B, then you would need less amount of force. So because in rotational motion, the more effective is force that is further away from the axle. So therefore there is introduced torque. Torque is force times the distance. So the distance here would be, let's call r small, and the distance here would be r big, and capital R. And therefore this torque here, torque B, torque A, would be F R small. So therefore this is small, this is a bigger one, and it produces more and it is more effective in rotational motion. Practical example would be like the one with the door, and this R can be called this is torque, not can, but is called lever arm. lever arm of the force. Here it is force. So examples are in everyday life. If you are using a wrench, let's say you have here a bolt, and you want to remove this bolt, so here it is. It would be the wrench, and you have the longer is the wrench. It's easier to remove the bolt because as this R increases, here it is the force that provides the wrench on the bolt, and as R increases, torque increases. Therefore, if you have it longer, you need less, it's easier to remove this bolt. Another one thing is if you are playing, let's say playing golf. So here it is the ball, and you want to swing the ball further away. Let's say you want to swing it further away, so somewhere far away you want to swing this. So you take the golf rod that would be shorter or longer. Of course you take longer. Because why? Because when player swings with this rod goes in what motion? If you swing with the hand, it goes in rotational motion. Swing. Yes? Swing in rotational motion. So when you swing, you produce, there's a rotational motion, that's what we were talking. So bigger R times F means bigger torque, and therefore this ball, if it is hit correctly, it goes further as compared to the short rod. Okay, so this torque is the equivalent of force. In rotational motion, as compared to that motion that we previously had, that was non-rotational motion in a straight line mostly, equivalent to force. So now what we have learned so far, we have learned that there was force in, let's call it motion in a straight line. So there was force, and here is rotational motion. So there was force, and here we have torque. There was acceleration. Here we have angular acceleration. There was speed. Here we have angular speed. Force, acceleration, speed. And there was mass. And here is some kind of more strange things. There is rotational inertia. So equivalent of mass. So this rotational inertia. So let's have an example where there is center. Let's say it's circle, something like circle, and there is an object moving in circle, has mass m, and here it is radius of that circle r, here it is phi angle, and here it is. Now there is external force acting on this mass. So external force acting on it. So in this case, we know that mass is traditionally is the quantity of inertia, and in rotational motion, as the torque has the length, the radius associated in it, as because it's torque is force times r, the length or the radius. So here the same r is as force times r is torque. So the same r is produce the same force at when it is applied at the distance r from the axle. It produces more effective motion. So the same here goes for mass. When mass is further away from the center at radius r, or from the axle, so the bigger is the inertia. So therefore in this, so we can write in this example, if we had F, it's Newton's second law for linear motion in a straight line. So if we had F equals ma, so force equals mass times acceleration. So mass was inertia. So in this case, we have for mass equivalent is torque. What is else? Else is for mass, it is rotational inertia. And here it is, instead of acceleration, it is angular acceleration. So it is the same, just these are the equivalents. Mass, rotational inertia, acceleration, angular acceleration, and force, it is torque. I have to write torque here. So torque is equal to this. So it is T, rotational inertia, that's right, I capital, and angular acceleration epsilon. So these are the equivalents. Now in this case, torque is what? Torque is F times R. Inertia, rotational inertia, how is calculated? I have not presented you. It is calculated like mr squared. Mr squared, so m and r squared, the further it is from the center or from the axle, the bigger it is, the more difficult it is to stop. And what else? Epsilon. Epsilon is delta omega, delta t, and omega is delta phi, delta t. So it is angular velocity. So it is angle. This is angular velocity. This is angular acceleration. Angular acceleration. Rotational inertia, torque. Okay, so here are the equations, and the last thing is conservation law. Conservation law. Conservation of rotational or angular momentum. Conservation law. So in linear motion, momentum is P mass times in this velocity, or in this case speed. Now in rotational motion, there is angular momentum. Angular momentum, and it is defined as capital L, and it is equivalent of mass rotational inertia, and equivalent of speed, it is angular speed. So rotational inertia and this is angular speed. So I times omega, this is, let's write once again, angular speed, rotational inertia, and this is constant. This is angular momentum or rotational momentum. So this is constant. So this is constant, L is constant. So if this increases, rotational inertia increases, this has to go down. And if this increases, angular speed, rotational inertia has to go down. So example with a skater is when, let's draw a primitive human being. If the hands are spaced widely apart, skater hands are widely apart. So it means that it's turning around this. So it's moving. Let's say it's trying to perform turning. Yeah, it's one turning. So it is, the skater is turning around his body axis. So around body axis, let's say the axis goes like this. So it's turning around his axis. So this is from the top, the view from the top. So view from top. And so this is what you see from the top. And in this case, when it's spinning around, I is large because mass is distributed further away from the axis or the center, from the axis that the turning is, from the, let's say, spinning axis, center. Here is axis. And I is bigger, so it means angular speed has to go down. I large, omega goes down. Now in different case, what's happening when we have the same axis? So the skater does what? The skater brings his hands close to the body. So what happens? Mass is distributed closer to the axis. This is the axis. And closer to the axis, and therefore the I rotational inertia is reduced, because closer to the axis, it means that R decreases. So it means that R goes, this was R large in this case. In this case, R goes down. Imagine R goes down. I is reduced, because it is I is mr squared. So I is reduced. Angular velocity increases, because angular momentum has to be conserved. So therefore it's spinning faster. That, let's say we show that it's spinning. Okay. View probably is like this written. I always mix up these W and V in the place. It doesn't matter. So here, what I wanted to show is it's spinning, its body axis is here, body axis is here. So when he brings arms further away, R increases, so R is here, increases. Rotational inertia is large because it's calculated like I is mr squared. Omega has to go down. In this case, he brings the arms closer, and that's why angular speed increases. I is reduced because mass is distributed closer to the axis, to the center of motion. So the same is with the diver. When diver wants to is jumping to the pool from high above, from high distance, from bigger heights. So then it is jumping, it's spinning, and he pulls his arms and legs close to him, and then rotational inertia reduces and increases angular velocity. So this example you may find in slides. So today it is everything, and we'll meet next time.